Hello, and welcome back to Mr. Warren's Audio Hood. This is the third episode in the series. Let's see what we will be discussing today. Today we will be discussing speaker dispersion patterns, balanced to unbalanced signals, phase and polarity, and last but not least, self-powered speakers. Every speaker cabinet has what is referred to as a dispersion pattern, and every component within the speaker cabinet has its own dispersion pattern. The shape of the cabinet and its interior baffling within the speaker box partially determine the dispersion characteristics of that cabinet, and the interaction among the various components also have a strong influence on this pattern. As I have mentioned previously, you have to walk before you can run, so we'll start with the simplest of speakers. In this case, we have a loose, open-framed component speaker. This is one of the type you would either use to mount in a ceiling plate or mount inside of a cabinet to make a speaker box. We'll start by examining what the published specifications for this component are. These specifications are for this actual speaker. Absent the speaker enclosure, you will notice that there's a specification for free air resonance, which basically means that, as with the tuning forks from the last episode, this speaker has a frequency at which it will resonate, typically in the form of sympathetic vibration. Although not very common in sound reinforcement products, there are devices which look exactly like speakers placed inside of cabinets, which are referred to as passive radiators, which lack a voice coil. It's basically a speaker minus a magnet minus a voice coil. They radiate sound by sympathetic vibrations from within the cabinet. Some consumer speakers and a small number of studio monitors utilize these. When a speaker cabinet is being designed, the free air resonance spec comes into play when designing the cabinet, as the speaker will operate at its most efficient near that frequency. As soon as that component speaker is mounted in an enclosure, the resonance of that cabinet has to be considered. If the cabinet's resonance point is too far below the component speaker's free air resonant point, it can create not only an inefficient design, but also could create a very unstable system. Basically, you would wind up blowing a lot of speakers trying to make a speaker box work in that configuration. This is, of course, primarily a concern at very low frequencies or in a subwoofer cabinet, but is also a key factor in designing some full-range cabinets. High-frequency components like tweeters typically have a free air resonance point as well, but since most components of that type are essentially enclosed within their own enclosure, they are not terribly affected by the overall speaker cabinet's resonance of itself. Speaker cabinets typically fall into three basic design types: front-loaded, horn-loaded, and folded horn type enclosures. The most common type of speaker cabinet you're likely to encounter at the entry level in the business is going to be typically a front-loaded speaker. Most common consumer speakers are also front-loaded. Front-loaded speaker cabinets are exactly what the name implies. All the components are mounted directly in the front face of the speaker box, in the same plane with each other. Generally, these type of cabinets are the simplest to manufacture. You build a box, you cut some holes in it, bolt some components in the front, and you have a speaker cabinet. A lot of modern speaker cabinets are made out of different types of plastics or composites. Molding a box out of plastic is certainly a lot cheaper than making one out of plywood or MDF. MDF means medium density fiberboard, sometimes erroneously called particle board. It's a finer grained material than particle board, although made in a similar fashion, but it also makes it easier to drill, cut, and mill with a CNC machine into specific shapes and patterns. You can pretty much mill and drill it the same way you would metal in some types of plastics. The main drawback to MDF is that it doesn't like to get wet. If it's not sealed correctly and it gets wet, it'll swell up and split. If you've ever seen cheap furniture that has gotten wet, you have likely seen this in action. Typically, most front-loaded speaker cabinets are a simple square-sided box, but there are also trapezoidal cabinets and stage monitor or wedge-style cabinets. And there are also multi-purpose shapes, which basically perform the function of either a wedge-style stage monitor, or they can be used as a speaker on a stick or as a front-facing PA cabinet. Generally speaking, like anything else that tries to serve two functions, boxes of a multi-function type generally do both jobs adequately, but not as well as a purpose-built cabinet that's only a wedge or only a front-facing PA cabinet. You have to compromise within the cabinet design to make it do both things. They do, however, add a great deal of flexibility to a typical production company's inventory, so you get one box that does two jobs. Another type of speaker is a horn-loaded cabinet. As you can see from the illustration, horn-loaded cabinets have the low-frequency components placed back inside the cabinet with a curved horn-shaped structure between those and the front face of the cabinet. Typically, horn-loaded cabinets are designed for throwing over a long distance, much more so than a front-loaded cabinet. The effect is because the horn in the low frequency acts like a sort of venturi, or as in that hose and nozzle illustration from earlier, when you're forcing things into a small channel and then expanding it as it goes out, it casts over a longer distance. Horn-loaded cabinets are not as commonly used these days as they might have been 20 or 30 years ago. However, some elements of horn-loaded designs are still found in some modern line array cabinets. Line array technology is something we will explore later on. Another, though rarely seen cabinet, is the folded horn speaker cabinet. This involves essentially creating a longer horn in a smaller cabinet space. If viewed in cross-section, a folded horn cabinet looks vaguely like a chambered nautilus. Some variations of this design are referred to as sugar scoops. Typically, these designs are intended to increase the throw in the low frequencies. Most professional speakers that are intended as PA speakers do not have tweeters, like your typical studio monitor or a hi-fi speaker might. Instead, the majority of common speakers you will find have a woofer and some type of horn, with what is referred to as a compression driver attached to the back of the horn, to deliver mid-range and upper frequency information. A simple tweeter is not nearly efficient enough to use as a high-frequency component in a main PA speaker enclosure. Thus, a compression driver/horn combination is used. A compression driver, when shown in cross-section, looks kind of like a backward speaker. The magnet is on the front of the component, while the diaphragm and voice coil are on the back of the component, as opposed to being on the front like it is on a woofer. There's also a back cover on the assembly. This back cover will typically have a gasket of some type between it and the rest of the assembly. This is where the compression part of the name comes from. This back cover becomes a compression chamber, sort of like the cylinder head in a combustion engine. When combined with a horn bolted onto the front of the driver, the whole assembly looks very similar to the venturi mechanism as in this illustration. Sometimes, perhaps a better example is a trumpet bell. If you were to remove the bell from the front of a trumpet, it wouldn't be nearly as loud. A speaker box with a woofer and a horn or a tweeter is referred to as a two-way cabinet or a two-way box. In most basic and very common PA speakers, that implies a passive crossover network inside the speaker cabinet, as from the earlier episode. In more heavy-duty professional speaker enclosures, each part of the speaker cabinet is fed directly by an amplifier with an active electronic crossover feeding the amplifier's inputs. This type of configuration is referred to as a bi-amplified system. While more costly in terms of extra equipment, such a system is inherently more efficient. There are two reasons for this. The first is that while a passive crossover is simple and inexpensive, they are also much less efficient. Those passive, meaning unpowered, inactive circuitry components in that type of crossover create what is referred to as an insertion loss by their presence in the audio signal path. Typically, that loss can range from 3 to 6 dB volts, depending on the design, the quality of the components, and other factors. The other problem is that most passive crossovers by nature are the most basic of filter sets. The circuit used in a passive crossover is what is referred to as an LC filter. Basically, L being the symbol for an inductor based on the word loop, a loop of wire, which is the most basic inductor, and C being the symbol for capacitor. They are so simple that the low-pass part is an inductor in series with a capacitor wired in parallel, while the high-pass part is a capacitor in series with the inductor in parallel. That kind of circuit is what is referred to as a first-order filter.
Knights of Ren. Ghouls.
No, not that first order. A first order filter means that it is limited to a 6 dB per octave filter slope, as shown in this diagram. A similar version of this is called an RC filter, where a resistor is substituted for the inductor. That version is usually found primarily in active circuits. The other issue with this is that with a first order low pass combined with a first order high pass, the filter slopes have a lot of overlap, which means that there will be a slight bump right around the crossover point, or a slight dip. The two sections will also have some symbiotic interplay between the overlap regions because the two circuits are interwoven. By putting an active crossover in front of the amplifier, we can put a much higher quality active circuit in line. With an active circuit, we get much steeper filter slopes at the desired crossover point, which means we can design the filters to work closer together and not have to worry about the overlap as much. This increases the efficiency of the cabinet by not sending wasted energy to the wrong component speaker. Whereas with a softer or shallower filter slope like a first order filter, there's a lot of overlap, so you wind up with a lot of low frequency information going to the horn component and a lot of high frequency information still going to the low frequency component. Inexpensive electronic crossovers are typically 12 dB to 18 dB per octave units, while better quality units are typically 24 to 30 dB per octave, which means a fourth or fifth order crossover, and really expensive ones are 36 dB per octave, which is fairly extreme. In truth, in this day, many amplifiers, even inexpensive ones, have DSP, which means digital signal processing, built into them that eliminate the need for external crossovers, since all of this stuff can be done within the amplifier itself, along with a lot of other functions, including equalization, limiting, speaker protection. There's all kinds of stuff that can be done with that. Other amplifiers have modular input cards that allow you to select an electronic crossover ahead of time and similarly have it in the amplifier unit. Other than the basic need to separate high frequency and low frequency information, as we explained in the previous episode, impedance is always affected by frequency, which means that a woofer type speaker will not efficiently reproduce high frequencies, and the compression driver / horn will not reproduce low frequencies. If we send low frequency information to a tweeter or a compression driver, eventually you will burn it out, or at the least warp the diaphragm. In any case, the component will be trashed. This is the other purpose of the crossover. Most high-quality professional amplifiers will also have a speaker protection scheme built in. It can be a simple analog circuit that senses overvoltage and disconnects the outputs or drops the levels down, or shuts the amplifier down. The DSP-controlled amplifiers can often have a menu available which has the correct parameters for specific speaker components. So if you know you have this particular model of speaker that the company that makes it also sells an amplifier to go with it, you can dial up that speaker model on the amplifier and it will already have everything set up and ready to go so that it works correctly with that cabinet. A lot of really advanced amplifiers have the ability to float the crossover point upward as incoming signals get stronger. That way you're taking more of the high frequency energy and spreading it into the woofer, which can handle it more so than spending lower frequency information into the high frequency components, which cannot necessarily handle it. As technology has advanced and amplifier designs have gotten lighter and more compact, powered speakers have become more commonplace. This technology ranges from little desktop speakers like you use with your computer up to large touring grade professional speakers. For demonstration purposes, we will work with 3 different units intended to be used as studio reference monitors. This first one is an Atom F7. It has a 7-inch woofer and a ribbon tweeter. The word ribbon tweeter refers to the tweeter using a thin metallized plastic film suspended in a magnetic field instead of a typical voice coil and diaphragm arrangement. The F7 and the 2 other speakers we will examine are all examples of self-powered speakers. All 3 of the units are bi-amplified units that have amplifiers and electronic crossovers built in. The published specifications for this speaker show a crossover frequency of 2600 Hz. Since I could not find the dispersion pattern specifications for this speaker, we will measure that using this simple rig. Knowing what a speaker cabinet's dispersion pattern is useful in knowing where to place the speakers within the room, and how many might be required to cover the audience within that room and where not to place them. This type of measurement is typically performed in an anechoic chamber. The reason being that reflections off of walls and other surfaces will skew the measurements. This studio space is reasonably well treated and reasonably damp, so that it's sufficient for illustration purposes, since we don't have the budget for an anechoic chamber. The rig uses a Lazy Susan mounted on top of a platform. We then have a reference mic connected to an RTA, or real-time analyzer, or spectrum analyzer, depending on what you want to call it. And you will see an overlay in the form of a protractor on screen. In the top of the screen, you will see the display from the RTA. As we rotate the speaker with the pink noise fed into it, we can see where its output at the microphone begins to fall off. Typically, when it falls off by 3 dB is what we call the fall-off point. If we multiply that angle by 2, we get the horizontal dispersion pattern of the speaker. To find the vertical dispersion pattern of the speaker, we simply turn the box on its side and repeat the process. We use pink noise for these measurements because for this example, it's the simplest method. If you put single tones in, you could measure the dispersion of the woofer with tones below 2.6 kHz. And with the tweeter, we'd measure the dispersion with tones above 2.6 kHz. If we were to manipulate this in a vertical plane, you could see some odd dips in the display. It has to do with the fact that the tweeter and woofer being a few inches apart when rotated on axis will produce a different arrival time at the microphone or in your ears. This effect is referred to as cone filtering and sounds like some kind of weird swishing. If you walk between 2 speakers like in a mall or a theme park or something that have overlapping coverage, you'll often hear this little swishing sound as you walk in and out of the coverage patterns between the 2 speakers. It's most particularly noticeable in the upper frequency range. A lot of guitar players will describe it as sounding similar to a flanger effect. This special tape measure you see in the illustration measures sound wavelengths by frequency. So the difference between the woofer and tweeter equate to a quarter wavelength at 3.15 kHz. That special tape measure is used for placing control room monitors in studios. Anytime you place a speaker near a wall, there will always be a cancellation point at a quarter wavelength of a frequency determined by the distance from the speaker to the wall. As in this illustration, using a piece of foam core to represent a hypothetical wall. In this example, that cancellation point would occur around 800 Hz. The following video clip is an example of cone filtering and what it sounds like. This was achieved by basically offsetting a copy of the same audio by a few milliseconds, much as would happen if you ran a signal through a external electronic processing box or a video recorder and back into a console and then combined it with the original signal. You'd get the latency delay or the offset delay between the 2 devices. We'll get more into that later, but you can at least see from this example what that sounds like. This next speaker we'll test is a Tannoy 600A studio monitor. You'll notice that this one has the horn, or tweeter as we want to call it, inside the center of the woofer. This type of speaker is referred to as a coaxial speaker. Like with the Atom F7, this speaker is also self-powered and bi-amplified. Since the woofer and tweeter are co-located, there's no time shift as the speaker moves. And as we measure it, the speaker has approximately the same dispersion in the horizontal and vertical planes. These speakers typically come with a pair of foam plugs that go in the round ports on the front. These foam plugs are referred to by the manufacturer as bungs. And yes, they do go in the bung holes.
I need CB for my bunghole.
They allow you to alter the tuning of the cabinets according to your needs. As we measure the fall off of the speaker, we see that it occurs at exactly 45 degrees, which represents a 90-degree horizontal dispersion. Because of the symmetrical design of the speaker cabinet, it will also be 90 degrees vertically, and the actual published specifications of the cabinet are listed as 90 degrees conical. The third speaker we will analyze is the Genelec 1030A. As we rotate this unit around, you can see that it has a fairly wide dispersion pattern. You will also notice that it has what is referred to as a soft dome tweeter. You can see that it has a slight horn lens attached to it. So how do you make use of this information? Well, if we take a theoretical room and a pair of imaginary speakers, and we need to figure out ahead of time where to place those speakers, this is how we arrive at that information. In this example, we have a pair of full-range speakers mounted on tripod stands. This is what we commonly refer to in the business as speakers on sticks. At the basic level of production, this is what you will most likely see 90% of the time in the general AV world. Most modern speakers made for this type of work will have top hat holes in the bottom of the speaker. The better units will have two different holes available in the bottom of the speaker. One hole will be a straight-on position, while the other will have a slight 7.5 or so degree down angle available for the speaker. Some people find that the down angle almost looks like a mistake, but it's actually very useful and very practical. That down angle position is my preferred route with this type of speaker if I have it, particularly in small hotel meeting rooms that have either untreated walls or have air walls very close in on the back side of the room, which usually aren't treated at all. They're covered in plastic over metal, so there's no absorption. It serves two purposes. Number one, you can direct more energy directly at more of the audience as opposed to shooting mostly over their heads in the straightforward position. To some people, it looks a bit strange, but it works very well. The other advantage is you can keep that energy from unnecessarily bouncing off the rear wall, which in some rooms can adversely affect intelligibility with all the slapback and echo bouncing around the room. So if we decide that our hypothetical speakers have an effective coverage pattern of 90 degrees horizontal and 60 degrees vertical, if we take our scale drawing of our hypothetical room with our given stage location and our given projection screen locations, where can we most efficiently and effectively place our speakers to best cover that audience in the room? As mentioned, our hypothetical speakers have the dual mounting holes, but not all speakers have that option. With those that don't have the option, you have to pretty much compromise your way into proper coverage. While you're trying to cover the audience adequately, you also have to be aware of where the projection screens are so you don't obstruct anyone's view of the screens or block the projection lens, projection cone of that particular screen. You also have to avoid having any spillage from the speaker onto the stage, because then you're fighting feedback problems by intentionally putting it too close or aiming it right at the stage. Ideally, your best location for a speaker is going to be closer to the downstage edge of a platform, as in this example. There are occasionally situations where you're stuck because of where all the projection screens are and the particular physical shape of the room, where you wind up with the speaker upstage, which is very undesirable, but it's still doable, it just limits you. The buzzword du jour in the industry these days is line array. This type of speaker arrangement is a line array. Basically, as it describes itself, it's an array of mechanically interconnected speakers hung in a vertical line. The idea is to control the coverage within the room by adjusting the splay or angle between cabinets, and adjust the coupling between the cabinets within the array by gain shading adjustments. This means that basically we will have the lower cabinets maybe drop down 3 dB from what the output level might be at the upper cabinets, as a simple example. There are some that are massively more complex than that, but you're not likely to deal directly with that caliber of system for quite a while, especially if you're just starting out. The concept of a line array stems from the line radiator speaker, which has been around since at least the 50s or 60s. There are some speakers that are classified as professional PA cabinets, and other speaker products that are classified as MI products, or musical instrument products, in that they are intended to be marketed to performing musicians. Lately, there have been a lot of column-style speakers, as shown in these examples, that are often marketed as line array speakers, which a lot of them, it's arguable as to whether they truly are. They might be a line radiator, but they're not truly a line array. In other words, you can't adjust anything between the different sections of the column, with one or two possible exceptions. The problem with most of these things is that they have ridiculously wide coverage patterns, horizontally speaking, like in the 180 to 200 degree range almost. This means that they're very difficult to use without getting some serious spill on the stage. This can be handy for a single guy playing a guitar in the back of the lounge so he can use the PA speaker as his monitor, but lousy for trying to do speeches and other information inside of a conference or a convention. For the most part, as you can see in this illustration, they're made from a whole bunch of 3 or 4 inch speakers mounted inside of a long column or a long tube. This also means that absent a lot of processing, most of them sound fairly similar to a large telephone. This is why most serious audio professionals say, do not buy sound equipment with your eyes. That's what lighting people do, and why wouldn't they? For my own taste, the worst offender in this is Bose. Their marketing angle is similar to the one they use with their little roommate speakers that you see sold as surround systems for home theater use. Those are marketed, and I don't want to sound misogynistic or chauvinistic, but they are literally marketed towards a high wife acceptance factor. In other words, the idea being that the average male wants to buy a big, powerful sound system for his home theater with speakers that look like that, which a lot of wives think are big and ugly, which I admit they're not exactly the most pretty thing and most feminine looking devices. So Bose's marketing angle was to sell a little speaker this big, the size of a baseball, made out of speakers that, again, sound to me like a telephone, that the wife won't complain about seeing hanging from the ceiling. Okay, but the big ugly speakers do sound good and they sound correct. Those little telephone speakers never do. Yuck. I'm sure the Bose cult will send me lots of nasty emails about this. You can make those things almost sound good, but you really have to work at it. That's all for this episode of Mr. Warren's Audio Hood. Please join us again next time for the next exciting episode of Mr. Warren's Audio Hood.